All right, geometry lovelies. Here it is, another geometry video. Yeah, so get ready just to have your whole life changed by your knowledge of geometry. Of course, I'm kidding. Hi, it's Miss Wait. Let's do this, shall we? Here's a warm-up. Uh, the best practice is to pause this video and dig into this and get as much of it done as you can on your own, because that shows you what kind of where you're at, what kind of thinking you have about these kinds of problems. And then I will be in here in just a second to guide you through it anyway. So just pause and see what you can do. Alrighty. So it looks like we have a quadrilateral with a couple of parallel sides. It looks like we have a 90-degree angle up in the top corner. It looks like one of the sides is extended out a little bit to create a bit of an exterior angle on that thing. We've got, it looks like we're trying to find the measures of angles 1, 2, and 3, and they are labeled inside that figure. So yeah, let's just get started. So with these kind of problems, sometimes you see it differently than me. Like I think we were talking about that in class the other day. You might see things differently, and so the way that I go about solving this you might be like, why are you doing it like that? Why wouldn't you do it this way? And you know, maybe you're right. I'm maybe not the most efficient mathematician. I just do it like I see it. And so that could be the same for you too. I mean, as long as we're getting to the same place, it kind of doesn't matter the path. So when I'm looking at this, really, I'm going to be solving for angle 2 first, because to me that makes the most sense. Here's why I'm saying that. Because what I recognize here is that I have a couple of parallel lines. I'm just going to extend them out just to kind of, you know, make them a little bit more clear. And then I also have a transversal. And again, I'm just kind of extending things out a little bit so you can see how it looks like those kind of figures that we worked on earlier in the year. And whenever you have two parallel lines and a third line that crosses them, as you do in this case, alternate interior angles are congruent. And so this angle here that's marked 60 and this angle here that has the 2, those are alternate interior angles and they are congruent. So for me, it makes sense to say that the measure of angle 2 is 60 degrees right off the bat. From there, I would get the measure of angle 1, because notice that angle 1 here and angle 2 here share both a vertex and a side, and their non-common side makes a line. That's what a linear pair looks like. They're definitely a linear pair. And every time you have a linear pairs are supplementary. In other words, angle 1 plus angle 2 equals 180. Well, I know what angle 2 is. It's 60. So the measure of angle 1 plus 60 has got to equal 180 degrees. Subtracting 60 from both sides, I get that the measure of angle 1 is 120. And so measure of angle 1 is 120 degrees. Recognizing linear pairs, that's going way back in this class. But that's okay, because these things can come in handy. That's why you learn them. So we've got a 120 degree angle at angle 1, and now it's just a matter of trying to find 3. Well, 3 is not going to be found using parallel lines, not going to be found using linear pairs. There's not a whole lot going on except remembering what you know about quadrilaterals. Now that's a quadrilateral right there. And what I want to find is this angle right here. But I know that this one is 60. I know that 1 is 120. I know that this one here is 90. And so all I need to know is what the sum of all 4 of those angles is, and subtract the other ones out and be able to figure this one out. Well, I've got a little formula for that. If I want to know the sum of the interior angles of any polygon, all I have to do is take 180 and minus 2 and figure that out, remembering that n is the number of sides. Well, in this case, there's 4 sides, so that leads us to the idea that we have 184 minus 2, which leads to 180 times 2 because 4 minus 2 is 2, which leads to 360. So we know that all 4 of those angles have to add to 360. So now we can say, well, if we take the measure of angle 3 and add it to, let's see, 90 plus 120 plus 60, we know we have to get 360 degrees because it's a quadrilateral, and we know the sum of the interior angles of a quadrilateral is going to be 360 because we figured it out using this little bad boy right here. So let's combine some like terms. Measure of angle 3 is kind of its own thing, but I can add up 90, 120, and 60 and combine all those together. So, oops, well, how do you do that on this calculator? Oh, it's all weird. Okay, 90 plus 120 plus 60 is 270. And that's going to equal 360. And then subtracting 270 from both sides gives us that the measure of angle 3 is 360 minus 270, 90 degrees. Nice. All right, very nice. Now, how many of you guessed that angle 3 was 90 degrees just by looking at it? I bet you did. It sure looks like a 90-degree angle, but if you had not included calculations, if this were a test, and you just told me the measure of angle 3 is 90 degrees just by looking at it, I would have marked you wrong. And here's why. You don't know that until you calculate it. There's no marking in that angle. You don't know. And so you got to calculate it first. That's how you figure that one out. Now, it sure looked like it was 90 degrees, but how do you know it's not, 89.94 degrees? That's not 90, and it sure will look like 90. So be sure you're either calculating or you're looking for markings. Okay, great. That's the warm-up. So here's where you're going to update your notebook, pause the video, and get that business done, and then we'll get started. Okay, your topic today, the last topic talking about polygons, is trapezoid theorems. We're going to take a look at one more type of quadrilateral, and we're going to find out some properties of trapezoids. That is the essential question. What are some properties of trapezoids? And your topic, trapezoid theorems, should go in the table of contents of your notebook. So, this says it's our second to last stop on the quadrilateral path. I have actually dumped a lesson. I don't know if you've noticed, but there's a lot of changes going on here at Central High School. And I just decided that this would be enough as far as this particular body of material. And so even though this says this is our second to last stop on the quadrilateral path, this is actually our last stop on the quadrilateral path. Soon there will be a quiz, and then we will start in on, I believe, some trigonometry. I'm super excited that we get to do that because it's pretty cool. So this is a trapezoid. You know one by looking at one. It's a quadrilateral, first of all. It has 4 sides. But the thing that makes trapezoids interesting is that only 2 of the trapezoid's sides are parallel to one another, and that is the definition of trapezoid. A quadrilateral with one set of parallel sides. So in this particular trapezoid, it would be those guys, okay? So that is a trapezoid, a quadrilateral with one set of parallel sides. Now, usually when you have a base of something, it's at the bottom, and so I could totally understand if you called this side the base of that trapezoid, and by the way, you'd be correct. That is a base of the trapezoid, but it turns out there's 2 bases in trapezoids, and they're both the parallel lines. So the base of a trapezoid is the parallel sides. To really say bases, because a trapezoid will have more than one base. So then you have what's called a base angle, and this should be kind of familiar from when we were talking about isosceles triangles. Base angles are the angles on either side of a base, and there's two sets of base angles. In this particular trapezoid, here is a base angle, and there is a base angle. And then there's another set of base angles associated with the other base. This one here and that one there. Those are base angles. And so I'll say that they are the angles on, and I'll put it in quotes, either side of a base. And then you got your legs. The legs of the trapezoid are the sides that are not the bases. And so you have a leg here, and you have a leg here. These are the sides that are not the bases. Alrighty, so that's a trapezoid. That's its parts. We're going to be referring to base angles and legs and all that stuff. So yeah, that's why we kind of went through this, so you could know what those words mean in terms of trapezoids. Now, we're actually going to be talking, first of all, about 3 theorems that involve a particular type of trapezoid. It's called an isosceles trapezoid. Now, when we talked about the word isosceles before, we used it in terms of a triangle. And when we had an isosceles triangle, there was 2 sides that were congruent to one another. And that's going to be essentially the case here in an isosceles trapezoid. An isosceles trapezoid is a trapezoid that has congruent legs. If these are your parallel sides or your bases, an isosceles trapezoid will have congruent legs. Isosceles trapezoid is a trapezoid whose legs are congruent. That's an isosceles trapezoid. And we're going to be looking at some properties of isosceles trapezoids next. So the first thing to do is to take a look at the isosceles trapezoid base angles theorem. And again, rather than writing it all out, I'm going to talk about it. I'll reveal the words. We'll talk about it a little bit. And then if you pause it and get it in your notebook, that's probably going to be the most efficient use of time. So here it is. Oops, I don't want to cover up the, there we go. If a trapezoid is isosceles, then each pair of base angles is congruent. If a trapezoid is isosceles, then each pair of base angles is congruent. So the second you know that a trapezoid, notice it's a trapezoid because it has one set, first of all, it's a quadrilateral, and it has one set of parallel sides. Also, the legs are congruent. That makes it an isosceles trapezoid. And in every isosceles trapezoid, this base angle will be congruent to that base angle, and this base angle will be congruent to that base angle. They won't be congruent all the way around, but base angles, each pair, will be congruent to each other. Here's the next one. The isosceles trapezoid base angles converse. So we're going to take what we just talked about and essentially flip it around. If a trapezoid has a pair of congruent base angles, then it is an isosceles trapezoid. So this is a way to tell if what you're looking at is an isosceles trapezoid, because if you have a pair of congruent base angles, then that trapezoid will be isosceles. It doesn't matter which pair. Maybe it's these two that you see. As soon as you have a pair of congruent base angles in a trapezoid, instantly you have an isosceles trapezoid. All right, here comes the third and final one for now, the isosceles trapezoid diagonals theorem. A trapezoid is isosceles if and only if its diagonals are congruent. And so this is a way of saying that as soon as you know that you're dealing with an isosceles trapezoid, you know that the distance covered by its diagonals is exactly the same. The distance between A and C in this isosceles trapezoid is exactly the same as the distance between B and D. In other words, AC is congruent to BD. In every isosceles trapezoid, that is going to be the case. And just like any other set of theorems, these are just little pieces of knowledge that you can use to calculate out problems. So let's do some of that. So we've got a keystone here in an arch, and it turns out that keystone is an isosceles trapezoid, and we want to find the measure of angle K, angle M, and angle J. What we know, first of all, is that it's a trapezoid. I can tell that because it has 4 sides, and 2 of those sides, its bases, are parallel to one another. I know it's an isosceles trapezoid because the legs, or the sides that are not the bases, are congruent to each other. And now I know all kinds of things about it. If it's an isosceles trapezoid, then its base angles, each pair, will be congruent to one another. Also, I know that its diagonals are going to be congruent too, but that's not really as useful because we're just dealing with angles here. I notice that angle L is 85 degrees. Well, if it's an isosceles trapezoid, that means that the measure of angle K also has to be 85 degrees. Because if it wasn't, then it wouldn't be an isosceles trapezoid. Because in isosceles trapezoids, base angles are congruent. So now it's just a matter of finding M and J. Well, we know they have to be the same, right? Because they're base angles of an isosceles trapezoid. If both of these are 85, and all 4 of them have to add to 360 because it's a quadrilateral, well, couldn't we just say that 85 plus 85 plus the measure of angle J, shall we call it X, plus X again, because the angle M has to be the same, has to equal 360 degrees. So let's combine like terms. 85 plus 85 is 170. And then since those 2 angles J and M have to be the same, we labeled them both as X, we can say 2X equals 360. Now let's see, we'll subtract 170 from both sides, and that gives us 2X equals 360 minus 170. 360 minus 170 is 190. And then the last thing to do, that means that both of these together measure 190 degrees, which makes sense. But now we have to split them in half because we have 2 angles, and we know they're going to be the same, so we can just split that in half. That's what this 2x is about. And we have x equals 190 divided by 2 is 95. And so the measure of angle M is 95 degrees, and the measure of angle J is 95 degrees. And we're done. That's how that first theorem helps you solve problems. You know that if it's an isosceles trapezoid, that the base angles are congruent. And so we use that idea to calculate some angles. So here's another way of looking at it. We need some parallel markings on here. So this is a quadrilateral. It has 4 sides. In that quadrilateral, 2 of the sides are parallel to one another, which means it's a trapezoid. Within that trapezoid, I notice that the sides that are not the bases, the legs, are congruent to one another. See this? Which means that it's an isosceles trapezoid. And the second I've identified it as an isosceles trapezoid, I know that the base angles are congruent. And that is what's helpful with this particular problem, because that means that this angle is going to be congruent to that angle. And this angle is going to be congruent to this angle, which is exactly how I'm going to build an equation. How do I know I need an equation? I'm being asked to find the value of x. And you don't find the value of x without an equation. So how can I set this equation up? Well, if those two angles are congruent, then I know that 5x minus 9 equals 2x. And it's time to start solving. Let's see. This is a little bit of a tricky one to get started on, but frankly, I would subtract 2x from both sides just to get those x over to the left. You could add 9 to both sides too. That wouldn't matter. You could do that. I'm going to subtract 2x from both sides. Don't freak out. It'll work out. Algebra works very predictably. As long as you're doing this, creating a clever cancellation, everything else is going to be okay. 5x minus 2x is 3x minus 9 equals 0, right? Because 2x's minus 3x's is 0. And now I'm going to add 9 to both sides. That creates this cancellation. I have 3x equals 0 plus 9, or 9. And if you started this equation any other way, maybe by subtracting 5x from both sides, or maybe adding 9 to both sides, eventually you got here too. You might have had a negative 3x equals negative 9 at some point, but we're going to get the same answer because your path was legitimate. It was just different from mine. So dividing by 3, x equals 3, and since that's what we were asked to do, find the value of x, that problem is done. Every geometry problem that involves solving for x involves an equation. How do you get that equation? The theorems. That's how you do it. Okay. So this one deals with the isosceles trapezoid diagonal theorem, which says that in an isosceles trapezoid, the diagonals, I couldn't think of the word, the diagonals are congruent. So let's work with this. If EG, this length right here, EG, is equal to or congruent to FH, is the trapezoid isosceles? Well, let's go back to our theorem, which says a trapezoid is isosceles if and only if its diagonals are congruent. And so we can say yes, because if those diagonals are the same, then it is isosceles, for sure. Now we're being told something about some angles. So let's see, what do we got here? Measure of HEF. HEF. Okay, this one right here is 70 degrees. Oh, that's my phone. Okay. Is 70 degrees. I'm going to mark it in there. And then FGH, I better do a different color. FGH is 110, is trapezoid EFGH isosceles. Well, in order for it to be isosceles, then those base angles would have to be congruent. In other words, this one would also have to be 110. And this one would also have to be 70. But does it work? If you add all those up, do you get 360? That's how we would be able to check. If we take 70 plus 70 plus 110 plus 110, we get 360. Yes, so it definitely works. This is an isosceles trapezoid as well. For the trapezoid to be isosceles, the base angles have to be congruent. If one of those base angles was 70, then the other one has to be as well. And if the other one was 110, then the other has to be 110. And those, all four of those have to add up to 360 because it's a quadrilateral, and all quadrilaterals sum to 360. So yep, it's an isosceles trapezoid. All right, friends. Hey, guess what? Your practice is not on Big Ideas Math. It's on the same program, Quizzes, that I use for our quizzes, but it's not a quiz. It's just an assignment. I didn't like the Big Ideas Math assignment, and so I went ahead and made one on quizzes for you. It's there in Google Classroom. Let me know if you need any help, you guys. Yeah, have a great day. Bye.